Okay, so considering that we're in the remote lecturing sort of paradigm here, I just wanted to kind of do a quick rehash of Tuesday's lecture. That was, oh, when was that? The 10th of March. We had a, we had a Zoom, but I didn't record it. And so I just kind of, for completeness' sake, I wanted to run through what we did on Tuesday. I'll do it fairly quickly here. And then my plan is for future classes, essentially to have it where we are recording the live sessions, essentially, and then posting them on Canvas. And so this is really just a review. If you're studying for exam number 2, you can kind of fast forward through this and take a look at what we did. So the kind of point of this unit here is to begin talking about runoff. And so as we sort of typically do, we have the kind of scientific basis of what we're doing in these hydrologic processes, and then we have the calculations. And so this is the kind of general overview, the scientific overview. And I'll kind of stop where we stopped in class on Tuesday, and we'll pick that up again next week. And so as a review, and I'm just going to keep the kind of annotations that I used on Tuesday. Hopefully that's not too awkward. So this is sort of where we're at in the entire water cycle. We've been kind of focusing a little bit more on stuff that goes on in the atmosphere, precipitation, evapotranspiration. Now we're really moving into the land phase of the hydrologic cycle. And that's important because sort of when people talk about hydrology, they really are talking about stream flow. They're talking about this part. This is a famous diagram on the right-hand side of the screen of water supply in the Colorado River Basin. And so that blue line then is indeed the stream flow. And as the kind of little annotations show, laws in the Colorado River Basin sort of were set up in the 1920s when there was this wet period that occurred in the basin. So they allocated water, they allocated 15 million acre feet of water, 7.5 to the upper basin, 7.5 to the lower basin. Little did they know, as I sort of drew here, that there would end up being a drier period, and this ended up being an anomaly. The kind of average conditions were probably a lot sort of lower than they thought back in 1922. This isn't necessarily a problem if the water supply isn't, if the water usage isn't that high, but you can see water usage sort of expanding out. And now there's a period where the actual use is sort of more than the river has to offer. One thing is that if you have storage, that's okay. But, like you want to also be able to replenish the reservoirs and that kind of thing. And it's not projected to get much better. Like these are sort of projections of what happens in the future. And you can see water demand is going to kind of consistently outstrip water supply. So we care a lot about runoff, basically, is the moral of the story. Okay, and so we've already talked a little bit about runoff in the class. And so when we did the watershed delineation, and then we kind of talked about this Strahler stream order, there's really 2 big rules. The first is that equal numbered streams come together to increase the number 1. So you have 2 2s coming together here, it makes it a 3. 2 3s coming together makes it a 4. But a lower order stream entering a higher order one doesn't change the order. And so you can see, as I've kind of highlighted here, you've got like little sub-basins all over the place here. This is a 3rd order basin that I've drawn out here. And that 3rd order basin going into a 4th order does not change the order, right? So the total order of this entire river basin is 4. And so, like stream order is one way to look at stream networks. Obviously, you can also delineate watersheds. We've talked about water balance in watersheds. And so, we're going to kind of talk about that most important term, that runoff term in water balances here in this unit. Water flows downhill, as you know, and so when we delineate watersheds, we just use the ground, essentially, DEM's contour maps to basically outline these watersheds, right? And you can see that you can have nested watersheds, and watersheds in general are defined by these outlet points. So the big watershed is defined by the outlet point down here. This littler watershed is here, and so forth and so on. And so, you know, we've already kind of worked on that a little bit. But what we're going to kind of talk about today is a different kind of classification that has to do with um, flow conditions, right? Okay. So, like I said, we've been working on the topography, but you know, now we're going to talk about something new, which is this idea of flow conditions. Okay. And so, we had a review question in class. The review question sort of was a little bit controversial, I suppose, because in reality, let's just kind of go through this. This is one of those true-false kind of questions. So for the first one, it's not true the DEM can be too coarse to create watersheds. Watersheds can be delineated at different spatial scales, so even larger spatial scales are fine. Hawk watersheds should be input into GIS in advance. I mean, if you're using GIS to delineate your own watersheds, you wouldn't need or want to do that. C was really the answer I was going for, this idea that you have these sinks or errors in the DEM. All of the water would sort of flow into those sinks, essentially, if you don't fix those errors. And so, you know, that was really the answer I was looking for. But, you know, you wouldn't be sort of wrong if you thought that you should identify the outlet of the watershed, especially based on what we just talked about, how watersheds are kind of relevant to the outlet. In reality, in GIS, it will actually sort of delineate the whole network for you, and actually it will show you sort of multiple subbasins that you can pick from. So you don't really identify the outlet first necessarily, but you do kind of identify the outlet at some point. So that answer was true as well. And it's kind of a good thought-provoking question anyway. Okay, so here are the sort of three different stream types, and I'll just kind of dispense with the silly animations here, you know, kind of all at once so that you can sort of copy them down. All right, and so actually these are probably not in the best order as we kind of talked about on Tuesday. The one that has the most flow most of the time would be the perennial streams flowing all the time, okay? And then you've got intermittent streams that are only flowing, or sorry, ephemeral streams that are flowing the least amount of time only during storms. And then intermittent streams where you're gonna have continuous flow sometimes, and then sometimes the stream beds are dry. So with intermittent flows, you can kind of see that in this picture where you've got, on the one hand, in the wet season, you've got like, it looks like a perennial stream. It is sort of a real river. It has water in it, but then it'll dry up part of the time, and then you'll see like a stream bed that has nothing in it, right? So, you know, this is kind of a seasonal thing. Ephemeral is like that it's normally dry, but sometimes when it rains, there's water in it. And then perennial is it's always wet, it always has water in it, okay? Now, what I've been kind of referring to then is this upper set of diagrams, which has to do with the relationship between the stream bed in black and the water table and the surface water in blue, okay? And we can start anywhere, but let's kind of start with the perennial. So you're looking at it downstream, right? So you're looking at this, you know, the stream bed here. The groundwater table is high enough where the groundwater table is contributing water into the stream, okay? And so, you know, even if you haven't had rain and stuff, the groundwater table might move a little bit, but you're always going to have water in the river. And you can imagine these really big rivers, it makes sense that that would be the case. There's a lot of flow in there, okay? Now, for the intermittent case is similar to the perennial case in some respect, because there's times when the groundwater is indeed enough to kind of fill the stream. But then there's other times where the groundwater table falls, and thus if the groundwater table is below where the stream is, essentially you don't have, you know, you don't have water. So like here, you can see, or well, you can't see, but potentially the groundwater table would have lowered. Now, with drought, with climate change, also with groundwater pumping, you can have situations where perennial streams end up turning into intermittent streams because like there's water that goes away. The Colorado River Basin, like near Mexico, is even in that situation. Okay, now with ephemeral streams, the big difference is that the groundwater table is so low as to never sort of rise up to even being close to where the stream bed is. So you have these violent thunderstorms, these, you know, that occur, say, in the summer in hot places. What will happen is those thunderstorms will dump a lot of water that will basically go into the stream bed and kind of just flow for a period of time, but not, you know, forever. So notice then in the diagram here, you see these arrows that indicate that that water is eventually seeping into the ground or flowing away, and it's not necessarily like immediately recharging the groundwater table. The groundwater table is in fact really low, and you know, like, it's not going to be rising. That's why I have the arrow and the X. It's not going to be rising to the point where it's going to be, you know, enough to make it a perennial stream. Okay. And so actually in the video, which I'm not going to kind of show here, but if you want to pull up the slides and watch it later, and I can link to it, well, I already linked to it in the slides, you'll see a little video of a scientist kind of talking about, and he's talking about that drying up problem where in California, they're actually seeing changes in the regime of, you know, these intermittent streams, for example. Now the diagram on the right here, it basically shows you sort of what can happen in these ephemeral streams. It's an arid place. You got this really intense kind of violent rainstorm that occurs here at the top of the kind of river basin, and then the water kind of makes its way through. And you can see these sort of hydrographs, we'll talk about hydrographs a little later, that kind of change in time, and you know, you can kind of see how it moves through so quickly. This is kind of one of those things where if you're in a stream bed and you see this coming, like, run, because you can kind of get swept away. You can have bone dry situations, and then you have rivers that are kind of activated. And then another thing we're going to talk about later is the idea that the kind of effective stream network that you see can kind of change in time. So maybe in the epicenter of the storm here, you could have actually seen something that kind of looks like a stream upstream of sort of where the perennial streams kind of are diagrammed. So all of those things kind of come into play. And later in the lecture, we're going to see the dynamics of sort of what happens kind of in a, like during a storm event. We'll focus on humid regions, but you can kind of tell that this is a very dynamic kind of situation that changes quickly in time. All right, so speaking of that, a hydrograph. Hydrographs are the complement of hyedographs. So hydrographs measure flow as a function of time, whereas hyedographs measure rainfall as a function of time. In fact, hyedographs are often sort of plotted upside down in a cutesy kind of way to kind of indicate the time series of the rainfall that kind of leads to one of these flow events, okay? And so, you know, as we're gonna see in a minute, how you kind of analyze hydrographs depends a lot on the resolution in time of the data, okay? If you look, like, this is, the purple triangles show the median daily stream flow. So the median daily stream flow is pretty boring in this part of the, you know, in this part of the year for this particular river in Pennsylvania. They usually have lower flow. So you can kind of tell during this particular event that occurred August 29th through September 5th in 2004, that they already were having more water in the river than they normally do. And then there's this kind of flat sort of section. And then something happened that caused there to be this really intense increase in flow in the river, and then it kind of tailed off. And so that whole thing is really what a hydrograph is going to show you. It's like a rain event that kind of looks like this. The river responds, okay? Now, one of the things, though, that is interesting about this idea of kind of time steps is the idea that sometimes hydrographs are reported as daily averages. If you have a daily average, when you have something crazy like this happen, what ends up happening is, as I kind of showed with the scribbles here, is that, you know, the average flow on August 30th would probably be somewhere around where the red line is. The average flow for August 31st might be somewhere around this line. So, you know, you're going to actually not be able to kind of tell what that peak flow rate was if you just have the daily average information. And that's why when you're working on something like flooding, you want to have these kinds of really finely resolved time series that have a lot of information about what's going on. Because if you've seen a flash flood or any kind of flood, it can change rapidly over the course of a day even, you know. And so to kind of emphasize that more, we have this other diagram that kind of indicates what's going on with hydrographs depending on the time scale. So the time scale in the upper left here is actually like years of flow. You can't really tell much about what's going on. You can tell general patterns, but every one of these events, you don't really see the details. This next diagram over in the upper right is a water year. So it starts on October 1st, goes to September 30. How many days are in September? You know, so it basically shows you what's going on. Now you start to see that more of that characteristic pattern. You can also then look at flows, you know, like maybe a daily record, you know, in the left, and even like kind of sub-daily information. You know, like when you take a look at, you know, this falling limb of the hydrograph is what they call it over here, you might not see anything interesting happening, but, you know, then when you kind of zoom in, you can see maybe this is local reactions to small amounts of rainfall. It's tough to kind of say, but lots of detail. It's like a fractal kind of thing almost. You know, you zoom in and you kind of see more in that kind of thing. So, you know, the time step that you're looking at really kind of changes depending on what you're doing. Sometimes for water supply, for example, you'll use a monthly time step where a lot of these details are sort of washed out. For flooding, you may use a very small time step because you care about the shape of what's happening, you know, when you have a lot of flow. Time steps are also, well, so I just talked about time steps, but there's also this idea of average versus instantaneous. And so, you know, like previously we were looking at, you know, what happened in a particular year or a particular month. You know, on the screen, you can actually see sort of maybe an average across a number of years, 1976 through 2005, gives you kind of a general pattern of what happens. This is for Colorado. You can kind of see this, the peak of stream flow that occurs, say, in May. Different models. This graph is basically a modeling exercise, and it's looking at like kind of how the models sort of capture, they're supposed to capture the black line, but different models essentially do better or worse at doing so. So average hydrographs are also something that is useful, especially if you're looking at the climate of a place or the kind of general trends of a place. Now, a couple slides ago, you saw that idea that you had a large amount of flow and then some kind of big jump. And there's a way that hydrologists kind of handle this. And this is this idea of what's called hydrograph separation, okay? And hydrograph separation basically tries to make a guess at what kind of processes are causing there to be flow in the reservoir or in the river. And I slipped and said reservoir because you can think about it like sometimes hydrological models are sort of as easy as essentially modeling the flow of water through a bucket, where if you pour water into a bucket and then you have a hole at the bottom of the bucket, what will happen is, you know, like the bucket will essentially make the flow kind of respond slower because the water has to go through the bucket, and then the hole kind of restricts the amount of flow that you can get out of it. And similarly here, it's like this hypothetical slow reservoir. So the ground sort of follows that same kind of procedure where when the water comes in, the ground kind of slows it down moving through. And so that means that in a hydrograph, you got this slow response. So take a look at the black line. That slow response that occurs, you know, could be from one of these kind of slow reservoirs, but really it's probably from the ground. And you can kind of do some mathematical trickery to essentially break up the big blue line essentially into two parts, the slow part and the kind of fast part. So when it rains, you know, like when it rains, like take a look in February, on February 1st, you have this large rain event, then the stream responds right away, you know, and the stream's response can be considered to add up those two parts, the slow part that's coming from groundwater and the fast part that's coming from, you know, runoff that's coming from the ground, right? Now, in reality, it's probably more complicated than that, but hydrograph separation gives us a way to kind of infer what's going on without having to worry about running complicated models and that kind of thing. And the drawings that I have here just kind of indicate that the hydrograph separation kind of algorithm actually has parameters associated with it. So in other words, like depending on how you tweak the numbers, the curve could kind of look a little different. The curve could kind of go up more, or it could kind of be more down here. In reality, you just have to kind of calibrate it to have it sort of match what you think is going on in the river, but it's not a perfect kind of science, right? And so just to kind of emphasize that, you know, you can really think about the fact that the runoff or, you know, stream flow that you see is a combination of two things: the base flow and then the quick flow, which is the response to a storm. And maybe I should be brave and try to show this video. I doubt this is going to actually work on the Zoom, but like if you can kind of, maybe we can just pause it. So in typical conditions, hopefully you can see this. Look at kind of where the water is, like where the banks of the river are. You know, banks of the river is kind of a silly thing because a bank of a river is sort of related to how much water is in it, right? And, you know, if you drain, you know, that kind of riparian area is going to look different. But in base flow conditions, you're going to see something like this. And then during a storm, it's like a nice little before and after. So there's the base flow. And then take a look at what the storm is doing and see how kind of like some of the stuff over here that was not inundated is now inundated with water, right? See where the you know, where the water comes up. So hopefully that's a good illustration essentially of what's going on, where it's like normally there's some water in the river, then when a storm happens, the river responds, basically rises and then falls again. Okay, so it's time now then to actually explain a little bit about what the hydrology is of that kind of thing happening. Okay, and by the way, you know, because like we talked about before with the perennial streams being fed by groundwater, this kind of thing, this explanation that we're about to go through is really for humid areas where the groundwater is close enough for these kind of dynamics to occur. So in infiltration, we talked about this idea that you're going to have water that's falling, rainfall that's falling on the surface, and some of the water is going on the surface, and then some of it's going to infiltrate and some of it runs off, right? Now there's a special name for this, which we'll learn in a second. But you know, you can kind of see that happening, and then you can also see then that you've got the water table down here. And so, yeah, the infiltration is occurring from sort of above, but then what is also happening is the water table is sort of moving up and down. So if the water table ends up intersecting the surface, like happens over here, you see this kind of return flow happen. So where the water table has risen such that now the ground is saturated. And if it's raining over here, it's going to actually, that rain is going to fall on wet soil and the water is going to run off, right? So that's what, and then that's what ends up contributing to stream flow. Okay, now, so that is happening. But like I said, the water table is going to move. So what we're going to do is we're going to kind of look at the kind of before and after. So this is a view looking down into the river of what happens before the storm, okay? And now we're going to look at the bird's eye view of what happens before the storm. And so you may have remembered when you were doing watershed delineation that, all right, well, I look at the ground and I sort of see that there are these valleys and stuff. And you may have wondered to yourself, well, isn't there water in there? You know, like, you know, the map shows that I have a stream in a particular place, but you know, like maybe there would be normally water in other places. And in reality, during a storm, that could happen. So by the way, that is why, you know, like on the maps, when you look at a stream network on a map, you're usually looking at a perennial stream, a flowing stream, a stream that usually has water in it. But you can see then that there's these kind of stream adjacent sort of regions that are upstream of where you are, where, you know, the ground could be saturated. There could even be intermittent stream beds that are occurring. that means that there could be water there, but there is not usually water there, right? And as you can kind of imagine with the way that I'm saying this, this is going to change, and you're going to see something different happen during the storm. Okay, so just to kind of go back and forth real quick, here you can see then that there are some regions whereas there is some saturation kind of occurring, right? But the system is kind of calm. It is going to be sort of shocked in a second. Okay, now, so take a look at that. And then you got a situation where when the storm happens, and the groundwater table rises, more of that area is going to be saturated near the stream. And there's actually a specific name for the runoff that is occurring because of that procedure. So the two kind of broad categories of runoff is infiltration excess overland flow, which we already talked about in the infiltration unit. The soil is saturated from above, the surface of the ground gets wet, and then the water kind of moves downward. But then because the groundwater table is also rising, the saturated overflow condition is where the ground is saturated because of the groundwater, right? So it is saturation, quote unquote, from below, and you can kind of see what that is like there. Now, either way, the soil is saturated and new water is going to run off. It just is like, where did the water come from that saturated the soil is the basic idea. When we look at this from a bird's eye view, then we'll see that now the stream network has really opened up, and those areas that were kind of saturated, areas that may not have even been connected to the stream network before, have ended up kind of turning into this sort of stream network that occurs kind of as the storm is happening. And so that's kind of a dynamic process. Then that eventually sort of recedes after the rainfall is over. And hydrologists, because they like to make names for things, have a name for this too. This kind of concept is the so-called variable source area concept. And so what that means is that source areas, and think about source areas as areas that generate this overland flow, kind of change as the storm is sort of occurring. So, and you can also think about soil conditions as part of this. So here you have some shallow soil in this kind of classically shaped watershed. And so, you know, some kind of saturation may be occurring near the stream, but everything's kind of normal. And there's a little superimposed hydrograph that's here in the upper right. So at time 0, everything's normal. At time 1, you start to have, notice the stream network actually kind of extends. Some of it's saturated here. This is kind of lighting up. And then as you get to the point where the flow is really starting to happen, you can see an even more extensive stream network. At the top, the whole stream network is kind of contributing. It's like, it almost looks like a different network kind of at the end than at the beginning. And then eventually it's going to kind of, it's going to kind of go away again. All right, and so here's a second review question. This one doesn't have as many problems, I say, than the first one did. So if you'd like to answer it, just pause the video. Okay, welcome back. Did you think through it? The right answer is actually C. So the SCS design storms basically set up different kind of time patterns for what's going on in a storm, and then you can scale them essentially by a design rainfall amount to get rainfall for design purposes. Okay, I think we're going to end there because this is where I'm going to pick up in class on March 17th. But for now, hope you enjoyed this video review, and you know, always reach out to me or come into the virtual office hours if you have any questions. Thanks.